In 2.3, we're going to be looking at modeling with linear functions. So we're going to do everyone's favorite kind of problems. We're going to do some word problems. And as we're looking at this, I want to kind of give you some processes and steps, because if you look at this problem and you go, I have no clue what to do, I want to give you some ideas and tips as you go forward. So first thing you want to do is you want to identify some known quantities. Read through the problem, see what information they are giving you, and make a little short list of it. Next thing you want to do is you want to assign variables to unknown quantities. Sketch a picture. If it tells you a rectangle, draw a rectangle. If it tells you a cube, draw a cube, etc. Number 3, if there is more than one unknown, find a way to write the second in terms of the first. Basically, if you can relate any variables, do that. The less letters we have, the easier it's going to be to solve. Number 4, write an equation. It may be necessary to use a common formula. If it gives you area of a rectangle, they assume you know area of a rectangle. If they give you perimeter, they assume you should know perimeter. And then number 5, solve it. So let's put all these steps together and let's see if we can approach this modeling of linear functions and do something with it. So it says a town's population has been growing linearly. So that's important. We know that what we're working with should relate back to what we have already been doing. In 2004, the population was 6,200, so we're probably going to need this piece of information here. 2004, 6,200. And by 2009, the population had grown to 8,100. So in 2009, it's grown to 8,100. If this trend continues, we're going to do two things. Predict the population in 2013, and when will the population reach 15,000? So let's scroll up here and let's look at our information and see how they're giving it to us. So first of all, they've given us two pieces of information. That in 2004, it was 6,200, and in 2009, it was 8,100. Whenever you're working a problem with years, you're always going to have some kind of base year as you go throughout. Rarely are you going to see that we're going to use that whole 4-digit number. Math people are lazy. We have formulas. We don't want to go in here and use 2004, 2009, etc. So let's let t be equal to 0 in 2004. Call that our 0. And let's let t be equal to, let's see, 2009 is 5 years later. Let's use 0 and 5, the difference between them, instead of using those 4-digit numbers. So right here, I can see that we have 2 points that have come about. And those 2 points are 0, 6,200. And then we also have 5, 8,100. And so if this trend continues, we need to figure out what's going on with this. So I'm going to take my 2 ordered pairs, and they've already said that it was growing linearly. So I got 2 ordered pairs. I know it's linear. I'm going to create an equation of a line. So we are going to write the equation with population as a function of time. And so let's find our slope first. We got 2 points. We're going to do your slope formula. Remember, that's y2 minus y1 over x2 minus x1. So it's going to be 8,100 minus 6,200 all over 5 minus 0. Subtract those. That gives you 1,900 over 5. So this reduces down to 380 people per year. So now that I have my slope between those two values, I just need to create the equation of a line here. So I'm going to go to my point slope form, and I'm going to say y minus 6,200 is equal to 380 x minus 0. So let's see, that gives me y minus 6,200 equal to 380x, and I can add that 6,200 over. So I ended up with a linear equation of 380x plus 6,200. So it says predict the population in 2013, part A. I'm just going to take that formula that I have, P of T, I'm going to switch it over to T, is equal to 380 T plus 6,200. We're going to find out what it is at 2013. Well, in 2013, that is 9 years away from our 0 value. Remember up here, we were looking at, we said we're going to let 0 be 2004. So 9 years later, so I'm going to say now P of 9 and plug that in through 380 times 9 plus 6,200. Use your handy dandy calculator, and that should give you a value of 9620. So predict the population, what it'll be in 2013, 9,620. Now for the second part, it says, when will the population reach 15,000? So we've done all this work and we created our equation. So let's just kind of pause and work on the next part. And so we're going to take what we've learned from all that work we just did. That was 380T plus 6,200. And for part B, we're going to predict when the population is 15,000. Well, we're going to take that 15,000 and we're going to put it right here with this P of T. So I'm saying I want my population to be 15,000. And so now let's solve for T and figure that out. So I'm saying minus 6,200. And so 15,000 minus 6,200, that gives me 8,800 equal to 380T, and divide by 380. So T is equal to 8,800 divided by 380, and that gives me 23.158. So roughly 23 years later, we'll be able to reach the population of 15,000. Now, if we need to figure out the year of that, remember, T equal to 0 was our 2004. And so if I go my T value of 23.158 years later, I just add that to 2004. So it looks like in the year, let's see, 2027, that we would reach that population of 15,000. Again, so if you need to kind of re-see this or you're a little lost still, kind of pause, rewind, walk through it again, and contact me if you have any questions. So in the first one, we're talking about the town's population. Let's look at example number 2. Example number 2 says, Anna and Emmanuel start at the same intersection. Anna walks east at 4 miles per hour, while Emmanuel walks south at 3 miles per hour. They are communicating with a two-way radio with a range of 2 miles. How long after they start walking will they fall out of radio contact? Breathe a little. If you feel a little lost, let's approach this again. Anna and Emmanuel start at the same intersection. Okay, so they're on a road. Anna walks east. So let's just draw a picture of that. So remember, think about your compass. Never eat soggy waffles. Thank you, 4th grade. So if Anna walks east at 4 miles per hour, so let's see, from this intersection here, she's going to watch east at 4 miles per hour, while Emmanuel walks south, so he's going to walk this direction, at 3 miles per hour. They're communicating on a two-way radio with a range of 2 miles. How long after they start walking will they fall out of radio contact? So if we kind of follow Anna here, Anna's walking this way as she's talking to Emmanuel, who's walking this way. And so we're okay with radio contact between the two right there. And now she's going to keep on walking, getting further and further and further. And he's going to keep on walking. And so if we think about the radio distance between them this time, it's going to be this far. So what this is doing is, you can see that this is creating a triangle. So as we're doing this and creating our triangle, we don't want to get the two children so far apart that when we create this triangle, the farthest they can be and not lose radio contact is 2 miles. So we've got to kind of figure out what's going on here. We know that 4 miles per hour is their rate. It's their rate of change, or their average rate of change. And so we're going to represent this by 4t. So she's walking 4 miles per hour, multiply that 4 by how much time has passed, and we get her distance. Then this we're going to represent by 3t. Again, how much time has passed, same amount of time has passed, so we both call those t. 3t, and so that should be our distance as we're moving south. Again, these were rates, and so I had to figure out a distance. So now I have a distance on my east, a distance on my south, and I have a distance on that hypotenuse. Now, whenever you're looking at your picture, in our steps over there, we said sketch a picture if possible. You can see that this is creating a right triangle. So it says use common known formulas. Well, let's think about this. So first of all, recall, and we've already used it, distance is equal to rate times time. So that's how we got that 3t and 4t. And then using Pythagorean theorem, we're going to set up an equation to go through this. And so that's one of those common formulas that you should know. And so I'm going to say, okay, Pythagorean theorem says take the leg, 3t squared, plus the other leg, 4t squared, and set it equal to the hypotenuse, 2 squared. So this gives me 9t squared plus 16t squared equal to 4. And then solve this out. So combine these two together. That gives me 25t squared equal to 4. And so divide by 25. That gives me t squared equal to 4 over 25. And then square root both sides. So this gives me t equal to plus or minus the square root of 4 over 25. But thinking about the square root of 4 is 2. The square root of 25 is 5. And when we're working at time, we only want positive. We can't go backwards. So t is equal to 2/5. Now let's relate this to what we're working with. You can see that, remember, this is our rate here, and this is in terms of hours. This is our rate, and it's in terms of hours. So that means this rate, this time down here, is in terms of hours. So it would be 0.4 hours. Or if we multiplied that by 60, we get in 24 minutes. So as these two kids are walking, they're going to lose radio contact after 24 minutes. So this is a great example of those steps coming into play. Sketch it out. Recall some of your formulas. Recall the distance is equal to rate times time. Recall your Pythagorean theorem. Those should be formulas that you know. Work slowly. Check your arithmetic. But as you're working through the homework, if you struggle or have any questions along the way, feel free to send me a Canvas message.